An open box is being built by using a 16 centimeter by 30 centimeter cardboard by cutting squares from 4 corners. What is the size of the side of the squares to form a box with maximum volume? First, we need to understand the question. We have a rectangular cardboard with dimension 16 by 30. So it has 16 width and 30 length. What we did now, we cut 4 squares from each corner of the side X. And this is the resulting diagram of the cardboard after removing those 4 squares. We then turn these extra sides such that this takes this form, a box, an open box without lid. And now you can see that since we have removed X, 1x from here and 1x from here, 1 square from here and 1 square from here, the length of this cube would be different than the length of this cardboard. It is actually 30 minus 2x. In the same way, since we have removed 2 squares from the width as well, so the width of the cube would be now 16 by 2x. Since the edge of each square was x, the height of this cube is x. So the dimension of this open box are so we need to find the value of x for which we have maximum capacity, maximum value of this box. So we need to figure out of what side of x the square should be removed so that the resulting box would have maximum volume. Remember, the bounds on the value of x are from 0 to 8. When x is 0, it means we are not cutting any edge, so x cannot be 0. And if we increase x by 1, like x 1, 2, 3, 4, 5, 6, 7, 8, it cannot go beyond 8 because when x is 8, the width would be 16 minus 2 times 8, which is 16. So 16 minus 16 would be equal to 0. Again, it will result a 0 volume. It means the value of x should lie between 0 and 8. Before applying any procedure, we can check it by a tabular form. So this is the length, width, height, length, width and volume, which is the product of these 3 dimensions. So in case we have 0 height, which is not possible, but just for the sake of sequence, we take 0 h, length would be 30 minus 2 times 0, which is 30, and width would be 16, and volume, which is the product of these 3 numbers, is 0. If we increase x by 1, so we take x, which is the height, 1, the length would be 30 minus 2 times 1, which is 30 minus 2, it was 28, and the width would be 16 minus 2 times 1, which is 16 minus 2, which is 14, and the product would be 392, which is the volume. So if we keep increasing x or the value of h by 1, we see that the length and width would be decreasing by 2 each time. So when x is 2 or height is 2, the length would be 2 less than the previous one, so it's 26, and width would be again 2 less from the previous width, which is 12 now. So product would be 624, and you can see that it is increasing. For height 3, the length is 24, the width is 10, and the volume is 720. But when x is 4 or height is 4, we see that the volume is 704. So it starts decreasing now, and after then it's keep decreasing until it's 0. So it means the maximum x would lie somewhere between 3 or 4. It may be at 3, or maybe somewhere between 3 and 4. So we can make another table and we'll take all the values between 3 and 4 and we again observe the pattern and we can decide at what number between 3 and 4 this has the maximum volume. But this method is very messy. You have to do a lot of calculations. Here we have only smaller numbers 30 and 16. What happens if we have bigger number? So this tabular technique is now effective, but it would take time. What are going to do? We using calculus to form a function which represent the volume of the box, and we will maximize that function and we'll see for what value of x that function is maximized. So take v is the volume of the box, which is length multiplied by width multiplied by height. Since length is 30 minus 2x, width is 16 minus 2x, and height is x. So now we can expand this function. This is not hard to expand, and you will see that this is just a cubic function. So expanding we get, okay, we need to find the extreme values. The process is as follows. We have to differentiate this function first, then we will put this derivative of the function equal to 0. We will solve the resulting equation. We get few roots. We'll again differentiate this function and then we'll put one by one those roots. The one which gives the negative value is the one which creates the maximum volume. So first we differentiate it. Y prime, this is 12 times x square minus 184 and plus 480 equal to 0. Okay, now we'll just divide it by 2 to get 6x square minus 92x and plus 240 equal to 0. We can again divide by 2. This is 3x square minus 46x plus 120 is equal to 0. And this is a quadratic equation. We can factor it out. This is 3x square minus 36x minus 10x plus 120 equal to 0. And this gives me, you check 3x factor out, x minus 12, and then if you can take x 10 factor out, it will be x minus 12 as well. So it has x minus 12 and 3x minus 10 equal to 0. Mean we have two roots, one and other is 3x minus 10 is equal to 0, or x is equal to 10 by 3. This value is not possible, as we had seen before that we have bound on x which is from 0 to 8. So x12 will create a negative width, so we'll definitely cannot take it. And this value seems logical, but we will complete our procedure. Y double prime would be then differentiating one more prime. It becomes 24x minus 184. And when x is equal to 12, v double prime would be 24 times 12 minus 184, which would be 104. So it is positive. It means this value will create a negative, a minimum volume. We'll check the other one, x 10 by 3rd, y double prime 24 times 10 by 3rd minus 184, and this will result negative 104, which is negative. It means this will result a maximum value. So it means x is equal to 10 by 3, which is 3.3 centimeter will result a box having the maximum volume. We can even find that maximum volume. The length was 30 minus 2x, which is 30 minus 2 times 10 by 3, and this is 30 minus 20 by 3, and this is 70 by 3. And we can take the width, which is 16 minus 2x, or 16 minus 2 times 10 by 3. If we simplify this, we'll get 16 minus 2 times 10 by 3, 28 by 3. And volume would be equal to the product of these three things. like height, which is 10 by 3, 70 by 3, and 28 by 3. 196,000 over 27, or it is 725.93 centimeter cubic. So this is the maximum volume we can get if we remove a sphere of length 10 by 3 centimeter from each